Hello everyone, my name is David Nedelkov, and welcome to Lab 5 of Physics 2211, Falling Slinky. Today, we'll explore the fascinating motion of a falling slinky. The purpose of this lab is straightforward but challenging. We aim to 1. Predict the motion of a falling slinky using physics principles and computational modeling. 2. Analyze whether the bottom of the slinky stays stationary as the top collapses. 3. Compare the observed motion, tracked from a real video, with predictions made by the computational model. Understanding this motion requires careful attention to external forces like gravity and air resistance and how they interact with the slinky's tension. Ultimately, we want to uncover why the bottom of the slinky appears to hover momentarily, even as the top falls. Now let's talk about the physics principles guiding this experiment. Like many of our previous labs, this one heavily relies on Newton's second law, also called the momentum principle. This law states that the change in momentum of a system is proportional to the net force acting on it. Mathematically, it's expressed as F net equal dp over dt. From this, we derive the velocity update formula and the position update formula. In addition to Newton's second law, we consider three key forces acting on the slinky. 1. The gravitational force that pulls the slinky downward. The tension force acts upward in the stationary phase, counteracting gravity, and the drag force, a resistive force proportional to the velocity squared, represented by F drag is equal to minus k v squared. These forces govern the slinky's motion in both the stationary and the falling phases. For the observed motion, I analyzed a video from Veritasium's channel. The slinky in the video has a mass of 0.218 kilograms, and the calibration was based on Derek's height of 1.75 meters. To collect data, I used Tracker to map the position of the slinky frame by frame. The initial conditions were as follows. Initial position minus 1.632 times 10 to the minus 3, 2.75 times 10 to the minus 4, 0, and initial velocity 0, 0, 0. As you can see, for the computational model, I plugged in the initial conditions that we discussed, as well as the mass of the ball, and I left the gravity as 9.8. In the first loop, I considered the first phase of the slinky, the stationary phase. The bottom of the slinky doesn't move because gravity is balanced by tension. Using the update formulas, the position remains constant. In the second while loop, I considered the motion phase. Once the top of the slinky catches up, the system starts falling. Now gravity and drag act together, and we calculate the changing in velocity and position using the same formulas. Here's a graph comparing observed motion and predicted motion. The computational model closely matches the observed data. The bottom of the slinky remains stationary during the initial phase, but there are small discrepancies due to 1. External forces like wind not accounted for. 2. Human error in tracking and calibration. Even with these errors, the model validates our predictions. Let's take a deeper dive into why this happens. Why does the bottom of the slinky stay stationary? It's all about the force balance. During the stationary phase, the tension force generated by the stretched slinky counteracts gravity exactly. This balance keeps the bottom in place until the top of the slinky reaches it. What would happen if we added weight to the bottom like a tennis ball? The outcome depends on the slinky's spring constant and length. If the tension force can still balance the increased gravitational force, the bottom will remain stationary. Otherwise, it will begin to move earlier. In conclusion, this lab provides a clear demonstration of how forces interact in a dynamic system. By comparing observed motion with a computational model, we validated the prediction that the bottom of the slinky remains stationary during the initial phase. The lab also highlights the importance of considering real-world factors like drag and external forces when modeling physical systems. Thank you so much for watching. This marks the end of our final Physics 1 lab.